It is February the 11th, and this is the 13th lecture in Lattice Boltzmann methods. So the topic of today is the efficient implementation of the cumulant method, with the content talking about floating point calculations, cascade or pairwise summation, and then we come to the Chimera Transform. So this lecture of today covers things that you mainly won't find in the publications, so in the literature, because for literature it's often considered to be too trivial. But if you talk to people, even in research, you will find that these things are not necessarily widely known and not necessarily widely understood. So I'm probably not making enough advertisement for what the Lattice Boltzmann methods in general and the cumulant method in particular can do. But last time, when we introduced the cumulant methods, we ended on this picture here, demonstrating that we can use the cumulant methods to do simulations at a much higher fidelity than the other methods that we introduced, in particular the BGK and the MRT methods. So these methods have increasing complexity in their collision operator in particular, but also their crit scale Reynolds number. So the crit scale Reynolds number, this delta, this would be the highest Reynolds number, u times the delta. So delta in this case is delta x. The highest Reynolds number that you can manage for at the resolution of for basically for one crit spacing, we're still getting reasonable results. So you can simulate at a much higher fidelity. This means so with smaller with lesser crits you get a more accurate result than with coarser crits on the BGK method. And this of course means you save a lot of resolution, and by saving a lot of resolution you save a lot of memory and you save a lot of operations. So however, this is a little bit of counterbalanced by the fact that you of course have more work to do in the cumulant method than in the MRT method, and in the MRT method you have more work to do than in the BGK method. The bottom line is of course always the further you go in this direction, the more efficient the method becomes. Because this, I said this is counterbalanced, which is not completely true. And the more accurate method is always the more efficient method. However, the challenges that we have with using the cumulant method is that, of course, the number of floating point operations in each node update. So this is basically what we have to do in one node update. You see this here. We have to distribute. We have the distribution. We compute central moments. Then we compute cumulants. Then we do the collision. Then we do everything back again. And then we do the streaming. Whereas in the BGK methods, we just have streaming. We use the distribution directly in the collision, so no transformation. And this is, of course, much simpler. So there are two things that we have to take into account when we talk about more floating point operations. One is that more floating point operations, of course, mean longer computational times. Fortunately, this actually is not that big a problem as you would imagine, because on modern computer data transfer, so this is basically the catching the information from the memory, this is much more expensive than doing the actual calculations. And in the BGK method is actually like this, that the the collision operator, I mean the computations during the collision, the floating point operations, they are more or less for free, because they are not enough to saturate the CPU, while there is a lot of information that has to be moved. And the good thing with modern computers is that they can move data while calculating. So calculate the operations, the floating point operations can actually be hidden by the transfer. And if there is more transfer than computation, then the computations are basically for free. And this then we call bandwidth limited. So LBM, in particular BGK LBM, is usually bandwidth limited. This means that the execution speed is just governed by how quick your memory access is and not how quick your CPU is. However, due to the fact that the cumulant method has so much more calculations to do, the cumulant method, unlike the BGK method, is actually compute limited. This means that the execution speed is governed by the number of operations that we have to do. And this also has another thing that we will discuss in this lecture, namely that when you have more operations, this does not only take more time, but if you have more operations, you also accumulate more round of errors. And this is something that is relevant for all explicit methods. It's not relevant for, or not so relevant for implicit method, because implicit methods use iteration to reduce their residual, and during these iterations, the round of errors from the previous iteration will be partly eliminated. This is the reason why iterative methods do not have the same problems with round of errors than explicit methods have, but the Lattice Boltzmann method is a strictly explicit method, and therefore we have here this kind of problems that we want to understand. And now we start with understanding round of errors. So let's understand round of errors. And there are two parts of this. So the first that we want to understand is data loss in the storage. So this is part one. Data loss while storing data. So let's look at our data. Our data is the distribution, or the distributions. The distributions F, I, J, K. This is our data, and these are our data. And this is a superposition. They are superpositions of moments. And the moments are, of course, the observable quantities of the fluid. So we have this moments M, A, B, C, yeah? And I'm explicitly now writing these raw moments because the raw moments is a linear transformation from the distribution, and since it's a linear transformation from the distribution, there's also a linear transformation back. So we can also write the distribution as a sum over A, B, C into some alpha, which is the inverse of the transformation, of the forward transformation, alpha ij k a b c. So we have that kind of tensor here, which we had to identify by inverting the system, but this is not important. The important thing only is that there is such a tensor and that we have a linear transformation between the moments and the distributions. Which means that all the f's are just some sort of sums of all the moments. Okay, now these distributions, for the reason of streaming, at least for the streaming, all these distributions has to be stored in floating point numbers. So, and you hopefully know that there are usually two kinds of floating point numbers. I mean, there are more of them, but these are the two that are usually used. So there's a standard IEEE 754, which defines how a floating point number is stored in memory. And now we look at the 32-bit float. This is a single float. You can also use 64-bit floats. Then everything that we discuss here will also be true, but only at a different magnitude. So let's look now at the 32-bit float first. So this looks like this, that we have one bit. I hope I'm audible because there's somebody cutting trees in front of my house. Can't do anything about this. So we have one bit for the sign. And then, so I'm not drawing this to scale now, but we have 8 bits for the exponent. And then we have 23 bits for the fraction. Okay, and in 64 bits floats or double precision floats, all of this will be larger, but the principle will be the same. So now our problem is that all moments share the same space in the fraction. You know, I'm very sorry that we have this noise in front of my house. I cannot do anything about this. I hope the recording will be not completely ruined by this. So all moments share the same space in the fraction. And now we need some things from our asymptotic analysis, namely according to our asymptotic analysis, they have different scales. The different moments have different scales. the moments have different scales. Okay, we could look at this in different scalings, but because the one that gives us the Navier-Stokes equation is the diffusive scaling, let's look at it at the diffusive scaling. So the diffusive scaling, again, this is delta t is proportional to delta x square, and this we specify by epsilon square. So then what we have here is an epsilon to the power of 0, which gives us the density of the fluid. Density, which is rho 0. Then epsilon to the first power, this gives us velocity. Our velocity is proportional to epsilon to the first power, yeah, so because this is epsilon u1, for example, so the first order of the velocity, yeah, this is multiplied here with epsilon in the scaling. And then we have the pressure or the stress. The stress is also, but I'm now just writing the pressure. The pressure comes with epsilon square and is now the delta. Okay, I'm now explicitly writing delta rho, which I did not write before. So this is the part of rho which is the second to the second order. So you could say that rho here would be rho 0 plus epsilon square delta rho 2. Yeah. So this is the way it is stored in memory, and then there's the errors. Yeah. So this is the expansion of rho, and u is expanded in epsilon u1, and then there is the errors in u. Yeah, so this is something that we do not want, because this is the error. Okay, but these guys are really variables of our system. So we have the density, we have the velocity, and we have the pressure. And they come at different scales in diffusive scaling. So we know, I mean, this is the point, and this is the point of asymptotic analysis, is that epsilon to the power of 0 is much larger than epsilon to the power of 1, is much larger than the epsilon to the power of 2, and so on and so forth. And this means, because our different variables, like the velocity and the pressure, come at different orders in epsilon, this means that the variables are scale separated. However, they still share the same space in memory. Okay. So they are scale separated, but they still share the same space. And in particular, I should probably write not in memory, but in the fraction. So specifically in the fraction of the same floating point number. So let's look at this fraction. So we have, so say this is our fraction that we have here, and here we have the most significant bit and down here we have the least significant bit. And the variables that are now stored here, so the largest variable specifies the exponent. Yeah, so the largest variable has to be stored up here, and the largest variable would be something that comes with epsilon to the power 0, and we have only rho that does this, so rho starts here. So then say we have an epsilon to the first order, which is smaller, so this comes later here, and that would be u, basically u to the first order. And then further still comes epsilon square, and this epsilon square, for example, things that come as epsilon square, this would be for example, the pressure, as we just said. But it would also be something like the velocity, the gradient in velocity. Yeah. So these things are also of second order, so they come here. And then there's also things that come to the third order, and this are most of these guys are then ghost moments. So all these variables extend from here to here. So the storage for from rho 0 starts from the beginning of the fraction and goes to the end. Whereas because the velocity starts here in the same fraction, it has only this space. The pressure has only that space, and the ghost variables, they would have even less space. And this basically means that this length of these scales here, these are the effective bits available for a particular quantity. So, and you see that for rho 0 we have a lot of space, whereas for velocity we have some less space, and for the pressure we have only half the space actually. Yeah? Let's look at an example. So let's consider the following case. We have rho 0, this is usually 1. Yeah? And now suppose we have our velocity scale in Lattice Boltzmann units. U is 0.01 in delta x by delta t. Yeah, so this is our scale, and you notice this is not particularly small. Yeah. It's not very small. So that would mean that in our our second order term here, yeah, which is now proportional to, this is the important thing, that the pressure is always proportional to the velocity square, which in lattice units then gives us, when we start from 0.01, so this is something of the order of 0.0001 that we have here. So this is relatively small. Let's look at these things here. Rho 0 is largest and defines the exponent. The exponent of the float. So this guy is stored in all 23 bits. So we can write this. There's actually one bit more because there's one implicit bit. So this here will give 1. Now I have to count. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay, I hope this is the right number of bits. So it's in binary, of course. So this is how we store rho 0. And this u by rho 0, this is 0.01, and this has to be stored in the same memory. Yeah. Now this starts, when we write this in binary, it looks like this. We have 0.000000. So I hope I have to take this from my notes now. And then we have 1, 0, 1, 0, 0, 0. I have to count again. 1, 1, 1, 1, 0, 1, 1, 0, 0, 0, 0, binary. So, okay, so this is how we store in the floating point number the velocity. And here we see we already lost 7 bits. 7 bits are lost due to the fact that we are storing the velocity together with the density. So for the pressure, what does the pressure do? Our pressure by rho 0. So we said this would be 0.0001, and this in binary is, now I have to count, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay, I hope that I wrote it correctly from my notes. I copied it correctly. If not, then we're probably missing one. Okay, this is how we store, so this is the B. This is how we store the pressure, and what we have now lost is 14 bits. So you see there's only 9 bits left. Yeah, so we lost more than we kept, even though the velocity that we started off is not particularly small. So, okay, let's write this down. In this case, which is only an example, of course, 11 bits of the fraction are lost at each order of epsilon. So each further, so in the first step, if for epsilon to the power of 1, we lose 7 bits. At epsilon square, we lose 14 bits. And now you can assume that at the third order, epsilon to the power of 3, we would lose 21 bits, which means we had only 2 bits left for order 3. Now, of course, this is only an example, and the number of bits lost depends on the magnitude of the epsilon first variables, because they define the magnitude of everything else. And this is, of course, the velocity to first order. And consequence is that the smaller the time step, the smaller is u in our units, delta x by delta t, and then the even smaller are moments of higher order. So, what we could do is to look what is the maximum ratio, maximal ratio of smallest to largest variable. So the largest variable is, of course, rho 0. And this we do by assuming that there's only 1 bit left to represent the smallest variable, which of course is completely nonsense. Yeah, so this would be a disaster, but let's take it for this discussion. So when we want to represent only the smallest variable with only 1 bit, then the ratio between the largest and the smallest is obviously 2 by the power of 23. Yeah, so this means that the largest variable is 2 by the power of 23 times larger than the smallest variable, because we have 23 bits. So, and this number is this number is 8 million. This is 8,388,608. So the largest variable can only be, or the smallest variable can only be 8,388,608 times smaller than the largest variable before it completely vanishes. And let's look at the another example. So if we have epsilon first order u, if this, for example, has a velocity magnitude of, say, 10 by the power of minus 5, so there's a small vortex somewhere which has the velocity 10 by the power of minus 5, then this would introduce a pressure of the order of 10 by the power of minus 10, which is, of course, already significantly smaller than 1 over 23, which means that in this kind of simulations, flows with velocities that are smaller than 10 by the smaller or equal to 10 by the power of minus 5, for example, delta x by delta t. These things, these flows, have no detectable pressure. Or, variation in pressure. So if you run simulation in single precision with the Lattice Boltzmann method, and you don't care about these things and notice how to implement them properly, you run it in single precision and you have a velocity of 10 by the power of minus 5 because somebody of your professors told you should use a small time step to get a good asymptotic behavior, then your flow will have no pressure. So if you want to plot the pressure, you see nothing but digital noise. Yeah? Nothing related to physics anymore. So this is, of course, a problem. And we try to mitigate this problem with something that we call conditioning. Okay, conditioning can have different meanings, but the meaning that we have today, or that we use here, is the conditioning is the reformulation of a problem with the aim to reduce numerical erosion. Numerical erosion is the build-up of round-off errors. Due to rounding. So there are, so poor conditioning so this is the motivation. I really would hope that they stop cutting the trees. I don't know why they are cutting the trees. They're just randomly cutting trees. There's nothing wrong with these trees that they cut. Poor conditioning results in a decline of accuracy at higher temporal and spatial resolution. Especially in temporal resolution. So you should usually think that the higher you resolve, the more accuracy you get, but due to round-off errors, you can actually have more errors and worse results than at larger larger time steps due to these problems with the round-off errors. And there are now many different ways to mitigate them, and the good thing to know is that usually the simplest things are the ones that are most effective, and but they are not enough. You also have to do some more complicated things, but the simple things are already the most effective. Yeah, so you pay first, you don't pay a lot, and then if you want to get more, you have to pay more and more and more. So the simplest measures to improve conditioning are usually the most effective. By the way, what most people simply do, I mean, the simple thing is you change from, maybe the simple thing is you change from single precision to double precision, or even to quadruple precision. However, this is not necessarily simple. I mean, this is simple to do in coding, but this makes your code, of course, much slower. So, but one simple thing that doesn't cost anything to do and is very straightforward is to recognize that this row 0, because it's zero ordered, it is by definition a constant. So, and because it's constant, it never changes. So if it never changes, there's no need to store it. And this we can use by redefining our distributions as as now delta Fijk. So this is just the change in this. This we define as Fijk minus Wij, where these Wij are the lattice weights. And they are, of course, of this kind that when we sum them up, we get row 0. So we, by subtracting this Wij from the distributions F, we eliminate the constant part such that the constant part in this delta Fij is now 0. So from a variable that is always positive, we have a variable that is either positive or negative, and which expected value is at 0. And what we do now is, instead of storing Fijk, we store delta Fijk, and now this will look now this way. If this again is our fraction, and here we have the most significant bit, and here we have the least significant bit. And now the thing is the largest variable is no longer an epsilon 0 variable, but it's an epsilon to first power variable. So we have epsilon u1 is here. Then we have here epsilon square, which would be epsilon square delta theta rho the delta rho to the second. So this is basically the pressure. This will go here. And then we also have epsilon 3, which would be the first ghost moments. So, and what we observe now is that for the velocity we have all the 23 bits. For the pressure we have much more than before, and for the ghosts also. So these are still our effective available bits. And they have become much more. Now, it is important to understand that this helps us. Storing delta F is helping us with not losing information during storage. However, this only works, and this is very, very important, and unfortunately sometimes misunderstood. It is not important, it is essential. It's absolutely essential that the well-conditioned state is preserved throughout all computations. So I had a student, and I tried, who I think I explained this problem to him, and that he has to store the delta F's and not the F's, and this is what he did. But then came the collision operator, and for the collision operator, because he didn't know how to transform the collision operator, before the collision operator, he added to the delta F the ijk in order to do the calculation. So of course, if you do this, you've lost all the advantages of previously storing the things this way. Yeah, so you have to eliminate the delta Fi, the constant part, not only from the storage, but you have to eliminate the constant part also from all calculations. Otherwise, there's no good in this. Yeah. Because what you have to keep in mind is that the accuracy of your methods, of your explicit methods, or the accuracy of the simulation in the end, is limited and governed by by the operation with the least accuracy. So if you have one operation in your system that is not well conditioned, yeah, so once you add again Wijk to your distributions or do something similarly stupid, yeah, all these these bits that you have preserved previously, they get lost. Because these operations come in a chain. And so you always have to remember the operations come in a chain. And the chain is only as strong as its weakest link. So really, if you actually implement a Lattice Boltzmann code or any other explicit numerical method, you spend most of the time, not with these fancy derivations, but you spend most of the time in conditioning them and try to arrange your calculations such that you minimize your round of errors. And the way we do this is now the topic of the second part of the lecture, namely the data loss in computation. So previously we talked about storing data, now we do actually talk about the calculation. Okay, and I've just introduced the this first simplification, but storing delta Fijk instead of Fijk, but for clarity of this discussion that comes now, we use the unconditioned. So in the end, you have to. So we use the unconditioned distributions in the following. So Fijk, but in reality, you have to combine all these steps with each other in order to get a good result. So first, how do we compute actually moments? Like, for example, the velocity. Say we have this naive computation of the velocity. So naive in the sense that you simply compute the velocity the way it is defined. So u is 1 over m0, so we have to normalize this, and here it goes for ijk from -1 to 1 into ifijk. So this would be, of course, we are assuming D3Q27 lattice. Okay, so this is the way we define velocity, and of course you can simply use this definition and implement this in your code, yeah, which would make sense in a sense. And this is a summation over 27 numbers, yeah, and okay, so there are several reasons why this is not efficient. First of all, small loops in modern programming languages are usually not very efficient in the first place. And the second thing is that of these 27 summations, actually 9 are 0 anyway, and so you would rather skip them than to simply add zeros. Yeah, because of course, there are 9 in this sum. I is 9 times 0, and 9 times -1, and 9 times 1. So we only use 2/3 of this calculation actually does anything in the first place. However, this is not the only problem, or not the problem that we want to discuss today. Yeah, so it means an efficiency problem, but it's not an accuracy problem. The accuracy problem comes from the way we sum up this Fijk. And then the important thing that you have to understand about round-off errors is that the most dangerous operation for round-off errors is also the simplest operation, namely this is the addition or the subtraction. So addition and subtraction, because they are combining numbers with potentially different exponents, they are the most dangerous things in the the operations that cause the most round-off errors. In comparison, multiplication does not cause that much round-off errors, but addition does. So the summation is the problem, really. Okay, so what is the cost in round-off errors of summing n numbers? This has round-off error of the order of delta times n, with delta being the value of the least significant bit. Okay, so we see with increasing number of operations that we do, we get a linear increase in the round-off errors, and this is proportional to the least significant bit. So for example, when instead of single precision, we use double precision, then the least significant bit will be much, much smaller, and therefore the build-up of the round-off error will also be smaller, but it will still be proportional to the build-up of round-off errors in single precision. Yes, it will just the prefactor of this will be smaller. Now the problem in Lattice Boltzmann is that we have many, many sums. So the computation of moments requires many sums like this. I mean, like computing the velocity, and computing cumulants even use more sums. Yeah, many more sums. So this is much more prone to round-off errors. Okay, now we want to repair this. And fortunately, there is a way to repair this or mitigate this at least, without causing more cost. Namely, this is a more accurate summation. Which is using the same number, which is important. So it's not more expensive, it's the same number. It's only more complicated to implement, otherwise it's not more expensive. The same number of operations. This is the so-called cascade. Sometimes it's also called the pyramid cascade, or the pairwise summation. Okay. And now if we want to implement the pairwise summation of computing the sum, we'll demonstrate this here. The first thing to notice is that this delta, so the least significant bit, is not the same for all the different distributions. So this should be taken into account. So the value of the least significant so the least significant build delta is of course not a constant here, yeah. It depends on the lattice directions. Due to the lattice weights. And in the D3Q27 that we like to use, we would have this W in the W111, for example. This would have 1 over 216. W110 is 1 over 54, and W100 is 2 divided by 27, and W000 is 8 over 27. So there's a bit of a difference between them. For example, you see that W000 is 4 times larger than W100, which means there's the least significant bit is also 4 times larger. There are two bits lost here. So okay, this means we have this delta from 0, 0, 0. This is larger than delta from 1, 0, 0, and this is larger than the delta from 1, 1, 0, and this is larger than the delta from 1, 1, 1. Which means there are separate classes of operation, and in order to further mitigate round-off errors, it is preferred to do summations within their particular class first. Yeah, so when you sum up distributions, you should not sum up a distribution of the kind that comes with the kind M111 together with a distribution W111. You should not sum this up together with a distribution that is W100 because they are completely of different sizes. So you should always sum up these distributions that belong to the same class by class, and later you sum up these classes. So this is now done like this. So we have for the computation of M100, we distinguish between these 3 classes. So we have the class where I, the absolute value of I plus the absolute value of j plus the absolute value of k is equal to 3. Yeah? So in this class, you do this f1jk minus f minus 1 minus j minus k. So these are just So these two distributions, they are exactly the one that go in the opposite direction to each other. And we'll take this for the second class too. So we have the class where this sum is 2. So there is one of these guys is now 0. So this is, for example, 10k minus f minus 10 minus k. This is one possibility, and we have f 1j 0 minus f minus 1j minus j and 0. This is the second class, and then there's the third class. I j plus k is equal to 1. So there's only one operation like this. This is f100 minus f minus 100. Okay, so these are the first operations that we do. Yeah, this is for the when we now what we do is we sum up things pairwise. Yeah, and the first pair that we sum up is here. So we have these pairs of distributions going in opposite direction. Yeah, we have, and this is step number 1. So because we have here k, j, and k, there's of course several of them. So we'll have this here. This operation here is actually done twice, and this so this j and k. So this also these things happen twice. Here this happens twice, and this happens twice. So we sum these guys up. So once we modified I, j, and k, and we did this twice, we sum up the previous pairs, and once we have done these, so this here is done only once. So this is, let's see, this is step number 2. Then there's a step number 3 where we sum up these pairs. And after we've summed everything in this group and everything in the second group, we sum the results of these two groups. This is step number 4. And then in step number 5, we sum up the results of these two steps together with the one of these two classes together with the one of the other class. Yeah, and in the end we have M100. Yeah, so this is we are simply doing the sum over everything, but we do the sum in pairs. And this is now done in 5 steps. Whereas summing up the numbers in one line would be 18 operations. Yeah, because the number of summands is n is equal to 18. So if we simply sum up these numbers in one line, we would have 18 summations. And then we would have round-off errors of the order delta times 18. So, however, here in this pairwise summation, we have only 5 steps of summation. So we only have the number of the the of levels of our summation is only 5. This is because the ceiling of the logarithm to the base 2 of 18, so we have 18 summons, and we split them up in pairs of 2, so there's 5 pairs, up to 5 pairs of 2. And the error in the cascade or pairwise summation is of the order of delta by the ceiling of the logarithm to the power 2 of n. Yeah? And as you see, this is usually much smaller than O of delta n. So from 18, so from delta times 18, we reduced our error to delta times 5. So it's almost 4 times smaller. The error in the round-off error in the pairwise summation is almost 4 times smaller than the one in the naive summation. And 4 times, this means you're losing 2 significant bits less if you sum things like this than if you sum things like in the naive way. Okay, so now this you have to do whenever you want to calculate any moments. But this is still not all. So we come to the last thing in this lecture, and this is the Chimera transform. So now we learned how to calculate the velocity a little bit more efficiently, or how to do sums a little bit more efficiently. Yeah. But we still have one problem. We do not only need one moment, but we need all moments. In particular, we need all moments if we want to compute cumulants. Yeah, basically, if we want to use cumulants, we need the transformation from moments to, from distributions to moments first, and then from moments to cumulants. So this means we have to get all of the moments, and this of course requires an entire transformation of distributions to in general central moments, because central moments, it's more efficient to compute cumulants from central moments than from raw moments, which is also possible, but even less efficient. And this means we have to do 27 such sums. And also we have to do the back transformation. Okay, so there's a lot of work. And now let's briefly look at the naive way of doing this. So again, we write the central moments, the Lagrangian moments, as K, A, B, C, and we define them as the sum. Now, in particular for the D3Q27 lattice, as Rij, the sum over Ij and K from -1 to 1 into Fij K, or the relevant part in the conditioned way. into I minus u divided by, now I have a little bit of problem with my letters because I'm running out of letters, u divided by this c by the power of a, j minus v by the divided by c, b, and k minus w divided by c by the power of c. So this c here, this c here is this index c, and the other c is, because I'm running out of letters, this is the lattice velocity delta x by delta t. So please do not get confused with me running out of letters. Okay, so we have, so all of all of these sums have 27 terms, yeah? So there are 27 distributions. And we have to compute 27 moments. So, which means naively we have to do a sum over 27 distributions 27 times. And this in each time step, and this twice in each, no, this at each lattice node in each time step, and we have to do it back, so we have to do it twice in each time step and at each lattice node. And this actually turns out to be the most expensive and also the most erosive, so the one with the most round of errors, the most expensive operation. In the methods. So, and to tell you the truth, when the cumulant method was first introduced, this completely killed the method in two ways. First, it was so expensive that it was completely unbearable, yeah, so that the method was too slow to do anything with it. And the other thing is, because there are so many summations upon summations, that the round of error built up was so disastrous that any improvement in accuracy could not be appreciated from this naive transformation. And it required an invention that we now call this Chimera Transform to actually make the cumulant method run. So without the Chimera Transform that we'll introduce in a minute, the cumulants actually don't work. Yeah, so this is the message. Yeah, and the question here is, of course, how to accelerate this. And this is, now comes this ominous Chimera Transform, this strange name, Chimera. So Chimera is something that so usually it is a mixture of one animal with another animal, so it's a beast of some sort. And here what we mean is the chimera is part distribution and part moment. So we do the moment transformation not in each direction at the same time, but only in a particular direction. So we write, so we have the indices I, J, K, usually for the distribution, and we have the indices A, B, C for the moments. And now I use Ij, Kij, which means in X and Y direction we have the moments, and I make here a small, the small line here, and then I write C, which means I have a moment in Z direction, but I have distributions in ij direction. So what I mean by this is that I split up the sum. I'm only summing over k, fij k, into k minus w divided by this c, and this by the power of c. So this is now something giving me something in between a moment and a distribution. So now I'm left with this strange chimera, which I do not want. So I want to have real moments. So what I do next is I take this guy here and do a moment in y direction. So I keep the x direction in moment in distribution form, and I'm just summing over j now from -1 to 1, and I have k ijk. So I take my chimera here and have this j minus v I c and this into b. So by the way, we have here, we still have 27 distributions. However, because the sum, we do a sum only over, we get only now what I'm writing here. So we still have 27 incoming f's, right? But we sum only over 3 terms. So we get only, we get 3 times, so we have to do it 3 times, yeah, but we have 27 times 3 in 3 terms. Then we do this here again, we have 27 times 3, and then we actually come, when we sum this again over, now what is it, over I j and not j, b and c, I minus u c by the power of now a, is it? Okay, now here again we have 27 times 3, and this means we have actually, so we have this 3 times, we have 9 times 27 terms. Okay, so this is 9 times 27 terms in sum, whereas the naive transformation, so this is the split up transformation, has 9 times 27, while the naive transformation has 27 times 27. So when we tried to publish this, we were told that this is too trivial to be published. However, this is you really have to understand that this is the reason why the cumulant method works. If you compute cumulants in the naive way, it is extremely more expensive, and in addition to this, it also has more round-off errors. Now, why is it so much more expensive? Yes, you could say that apparently this is just 3 times less expensive, but the reality is even more. In reality, we see even more operations, because we not only have fewer terms, but we also have fewer operations within one term. within one term each. And the terms in the naive transform, and therefore the savings are even higher. And because it is a bit complicated, what we did is we used the computer algebra system, implemented this transformation, and counted the operations. So we counted the operations, we used the naive form and we used the Chimera form. And we counted how many additions do we have and how many multiplications did we have. So the result is the following. We get, for the naive operation transformation, we get 1,482 additions. So you see, this is not completely trivial. This is in every time step, at every grid node for one transformation. And remember, we have to do two. We have to forward and backward transform. We have 1,482 additions just in the transformation. In the naive way, in the Chimera way, we have only 270. Multiplication, similar. We have 1,452 in the naive operation, and here we have only 162, which you see is we have only 1/5 the number of operations. So, and then there is another advantage of this, namely that the Chimera transform is a cascade summation. And because it's a cascade summation, the round-off errors are much smaller than in the naive transformation. And actually, this was even the bigger problem, namely that the naive transformation is so inaccurate. And what we have observed, what we have measured, is that a single naive transformation so this is one transformation. This is one time step, one lattice node. One time step. In one time step, you can lose 10 significant bits just by this transformation. Oh no, I should say you can lose 10 significant bits more. It's not so that the Chimera transform doesn't lose anything, but you can lose 10 significant bits more than the Chimera transform. So the way you measure this is you do the forward transform and then you do the backward transform and without collision. And so forward and backward transform should give you the result that you had before. And then you subtract these numbers and then you see what is the error. And what you see is that the naive transformation loses 10 bits more in a single time step at a single node. And now remember that you had that we have only 23 bits. And if you lose 10 of them in one time step, then it's pretty logical that this doesn't work. Yeah, so the naive way of implementing a cumulant method, unfortunately, we tried this for a long time. This doesn't work, at least not in single precision. And the reason why this method nowadays works is exactly for using this Chimera transform. By the way, the word Chimera transform may sound a bit strange. In reality, what this is basically a kind of a fast Fourier transform. And the interesting thing about a fast Fourier transform is that it is also a pairwise summation algorithm. So it uses this cascade summation through its algorithm, and therefore has much fewer round of errors than a naive Fourier transform. Yeah, so it is apparently more easy to sell things for being fast. So they call it fast Fourier transform instead of calling it the accurate Fourier transform. Yeah, but actually, from a practical point of view, what may even be more interesting of the Fourier transform that it is fast is that it is accurate. Yeah, so the fast Fourier transform is an accurate Fourier transform compared to the discrete Fourier transform, which is a naive summation. Yeah, because the naive summation has this build-up of round-off errors, while the fast Fourier transformation does not have this. Okay, 3 minutes over time. Thank you for listening, and we see each other next week.